Let's now connect the LCD display to our microcontroller. The original Hitachi display driver chips were designed decades ago when microprocessor control lines were at a premium. Hence the reason why they are capable of 4-bit mode. And now with the advent of microcontrollers, where the focus has been on keeping the size down and thus the number of pins, these LCD displays are perfectly suited for microcontrollers. On our microcontroller, we will need 4 pins for data lines and 2 pins for the RS line and the E line. We'll just tie the RW line to ground, as we will only be writing to the display. Now, port C has 6 pins we can use. Port A has 5. Notice there is no RA2. However, there is another caveat with the specific design of this PIC. Because of the USB capabilities, there are limitations on what the pins could do. Basically, they traded off smaller capabilities for one huge capability, that of having native USB communication. When we read up on the description of the Port A register in the PIC datasheet on page 131, notice what it says. Port A is a 5-bit wide bidirectional port. The exception is RA0, RA1, and RA3, which are input only, and its tri-state bit will always read as 1. Now, to be honest, I missed this when I was building up this next circuit, and it had me stumped for the longest time because I was trying to use RA0, RA1, and RA3 as outputs. So keep your eye on that in the future, because it'll mess you up. So we can use strictly port C for everything, as those pins can all be outputs, and we have just enough pins available for the LCD display. But instead, what I did in my code, you can write yours differently, obviously. I used port A for the control lines and port C for the data lines. The schematic is in the downloads, as well as several code samples you can use. I have tremendous confidence in your capabilities at this point, so if you wish to modify how the display is driven, you can. You can tie all of the lines to port C, and you can just alter the code accordingly. There's some things we need to account for before we build our code. Our PIC is way too fast for the LCD display. We now need to take into account a fairly important part of digital electronics called timing. We will often have to take special action with digital electronics, especially for things like analog to digital conversion or driving loads external to the processor, etc. The LCD display is no different. Now, this is all buried in your LCD display datasheet, so you can read it, but I'll save you some time. There are 3 critical timings we have to watch out for. The first one is the fastest we can write or read to the chips. Basically, before the enable line goes high, the data on the data lines must be present and stable. That is, any glitches in the signal must have leveled out for at least 200 nanoseconds. Now remember, this is a digital circuit. It's so fast it can read the bounces on your switches. So if there's any noise on your signal, it can actually count that noise. Once the enable line goes high, it must stay high for a minimum of 450 nanoseconds to load the register. Then, as you saw when you built up the manual control circuit, it registered the data on the screen when you released the push button. When you released the push button, the E line went low. It has to stay low for a minimum of 500 nanoseconds before the next time the E line can go high. So that means just to send one nibble of data, we have to take our time, a minimum of 450 plus 500 nanoseconds, or just round it up to 1 microsecond. Now, that's very fast. However, our microcontroller is way faster. To figure out frequency, we invert the time. 1 divided by 1 microsecond equals 1 million hertz. So in order for our PIC to be able to communicate with our LCD display, we got to slow it down. Because right now, it's running at 16 million hertz. So we have a couple of options here. The first option is to put delays into our program whenever we write something to the display. We can put the data on the data lines, then send a high on the E line, then run a subroutine which simply delays the processor for 1 microsecond, then comes back and sends a low on the E line. We now run that subroutine again to delay the processor another microsecond before we load the data lines or do anything else. Now, it can be tedious, but this works. To keep things simpler, we're going to go with option number 2. Because we have full control over the microcontroller, you'll remember we can set its clock speed. We already set our clock speed with the OSCON register, and if you turn to page 75 in your PIC data sheet, you can see all the options you have for clock times and how to set up the OSCON register accordingly. Now what we'll do is we'll set the speed to 1 megahertz. This guarantees that our control line times will meet the minimum times for the LCD display and will save us a whole pile of programming. Now this is especially true when you consider that you'll never get any outputs sent out on the PIC data lines in less than 2 clock cycles per instruction. So you could probably run at 2 megahertz and not have any problems because the instructions could only be carried out at a maximum of 1 million instructions per second. So if you want to run the processor at higher speed, you can do that. Just bear in mind, you have to take the maximum speeds into account for the display. So I'll set up my clock speed to 1 megahertz. So when I look at page 75, I see that to get 1 megahertz on the internal clock on my PIC, I set the OSCON internal oscillator frequency select bits to 1011. Now, bit 6 and 7 are the clock multipliers, so you can really crank the speed of your PIC right up to 48 megahertz if you want. But obviously, we want to go the opposite direction. We want to slow it down, not speed it up. So we turn off the multipliers by putting zeros on bits 6 and 7. Bits 0 and 1 choose what kind of clock we want to use, and we want the internal oscillator clock. So we need bit 1 to be high, and bit 0 doesn't matter anymore. So from all of that, we can deduce that we need to set OSCON to 00, 1011, 10. So my setup code will be all the same as before, except I will be changing this line right here, and we'll be changing the byte to 0010, 1110 to set our oscillator to 1 megahertz. The second critical timing issue has to do with those commands you sent to the LCD. Remember setting up the display by turning it on or moving the cursor. Each command takes time. Now, most of them take about 40 microseconds, but some, like clearing the display or moving the cursor, because these involve several steps, they can take anywhere from 40 microseconds to almost 2 milliseconds. Now, again, not a lot of time, but in the digital world, it sure is a lot of time. So every time you send an LCD command, you'll need to delay the PIC. Just keep things simple. Let's plan on a 2 millisecond delay. Now, remember, we already built these utility delay subroutines, right? Except now we've changed our clock speed from 16 megahertz to 1 megahertz. So our delays will now be 16 times longer than the last time we used them. Now, no biggie, we just need to remember that. The third critical timing on our LCD display is its initialization time. Now, this only happens once, but we need to account for it. Again, this information is in the data sheet, but it's a long time. When you first power up the LCD display, the driver chips go through a whole series of steps to get everything up and running. Now, this takes forever in digital time, a minimum of 15 milliseconds. That's almost 1/5 of a second. That's like start, stop. There, that was about 1/5 of a second. Even when you've slowed your PIC down to a measly 1 million times per second, obviously you're going to have your PIC stand around and do nothing for a while, waiting for the LCD display to finish booting up. So with that in mind, let's take a look at our sample code, the LCD code download. I put in some comments here regarding the GPRs, those general purpose RAM memory locations, which we were using for our utility delay loops. In this code, we're going to use 4 of the 16 GPRs available. So I've just made some notes in the comments about what GPR is used for what. This is partly so I don't inadvertently use the same register for 2 different jobs. We then go through the setup fuses, and here's our OSCON, which sets up the clock to 1 megahertz. Now we get down to business. Let's set up port A as outputs, and even though bits 0 through 3 are inputs only, it doesn't hurt anything to try and set them up as outputs, and it saves us some lines of code, because now all I do is clear the tri-state A register instead of loading the W register, transferring it over to tri-state A, etc. We set up the bank for latch A, and don't forget this. Forgetting to change the bank is one of the most common mistakes you'll make. We clear all the outputs on port A. We only have 2 control lines wired into port A, the register select line and the enable line. We now set them both to 0 to kick it off. Now, at this point in the program, we have just powered up. So while the PIC has completed all of these tasks, the LCD is still doing its initialization, which takes forever, 15 milliseconds if you recall. So we need to wait at least 15 milliseconds. We call our utility delay subroutine, which you are already familiar with way down here. It's the exact same subroutine we've used before, but bear in mind, we're now running at 1 megahertz, not 16 megahertz. So this whole delay now takes approximately 0.8 seconds. Now you can change these numbers if you want. I was just lazy. We just needed to delay a minimum of 15 milliseconds. If you delay longer, that's perfectly fine. So I just copied and pasted the original utility delay in and left it as is. It exceeds the minimum delay we needed. That was all I cared about, as I wasn't in a hurry to get this LCD display up and running or anything. So we delay 0.8 seconds and then head back to where we left off. We now set up port C as outputs, and then we set up the display for 4-bit mode and then 2-line display mode. Now this was done exactly the same way you did manually driving the display. Now this may be a bit confusing at first. Just remember what we've done with the wiring. We have bits 0 through 3 on port C connected to our data lines D4 through D7 on the LCD display. So when we send a byte into port C, these 4 bits don't do anything. They don't go anywhere. They're not hooked up to anything. But we have to put the upper nibble in there for the sake of the compiler. These bits here are strictly placeholders from when we load up port C to ensure these 4 bits, which are the important ones, get sent to bits 0 through 3 on the port. Otherwise, the compiler might get confusified and spit out errors like, hey, I need 8 bits, you only gave me 4, what's going on here? So if you recall, to set up the LCD for 4-bit mode, we sent 0010 to the LCD display. This was the upper nibble of a function set command, exactly like what we did with the wires in the last section. Just this time, we're sending it using the PIC. So we send out 0010 on port C, and that number is now sitting there. So what else do we have to do to make the function take effect? We have to have the RS line at 0, which tells the LCD this is a command, and then we pulse the E line. Well, we've already got the RS line at 0. It's coming off port A, which we already cleared, right? So now we just need to pulse the E line. I did this with a short subroutine I called pulse E, which is down here. The pulse E subroutine switches the bank for LA for latch A, very important. We set bit 5 high on port A, which is the E line. I then throw in 2 instructions called no operation. This is literally an instruction that does nothing. So why put that in there? It's because every single one of those lines takes time because the program counter has to count up a minimum of 1 clock pulse. I put these no ops in strictly to delay the processor just a few more clock cycles, just to make absolute sure that the enable line is high long enough for the data to register. We then clear bit 5 on latch A, on port A register, which sets the E line to low. We wait around for a few more clock cycles just to be absolutely sure that the line stays low long enough for the LCD driver chips to get ready for the next data. We now return to where we left off. We've now sent the command for 4-bit mode and pulsed the E line. So now the display is in 4-bit mode. Every single bit of data we send now has to go in 2 nibbles. The upper nibble first, lower nibble second. So we're still in command mode, and we'll now send the 2 nibbles we did before in our manual drive circuit. So we leave it in 4-bit mode and set the display to 2-line mode. Now remember, there's nothing connected to these bits. So we first send a 0010, pulse the E line, then send 1100, and then pulse the E line again. Then we want to turn the display on and set the cursor to underline and blinking again, just like we did before. That command was binary byte 0000 1111. So we send it in 2 nibbles. Here's the first nibble. We then pulse the E line, then the second nibble, and pulse the E line again. We now have the display turned on, a blinking and underlying cursor, and we are now ready to write information to the display.